What's wrong with these graphics for paired data? Well, it's not that easy to find pairs of twins such that one has schizophrenia and one doesn't. Why would we do that? Well, because probably there's a correlation in the brain size or the measurement of some part of the brain within twins. So you might have two really, really, really big guys, right? Maybe they're like football players or something, right? One with schizophrenia, one without. They probably both have big brain sizes, but it's possible the one with schizophrenia might have a slightly different measurement than the one without. And then you might have two other people who are very, very petite, right? Twins who are very, very petite. So both of their brain sizes will be way smaller than football players. But maybe there's a pattern, right? Maybe the one with schizophrenia has a slightly different brain size than the one without. So the whole point of going out and finding these elusive twin pairs where one has schizophrenia and one does not is so that you can take into account the fact that there's a correlation between the brain sizes of twins. You want to know what's the difference within each twin pair. Like, was a schizophrenic twin's brain bigger or smaller than her sibling? Not just let's group all of the people who are affected and all the people who are not, right? In this box plot, you can't tell which affected person matches up with which non-affected person. In these histograms, you can't tell which affected person matches up with which non-affected person. So you need to come up with a graphic that takes into account the pairs. What kind of graphic am I thinking of? Well, one thing you could do is make a scatter plot where here's the affected twins' brain sizes and here's the not affected twins' brain sizes, and you make one dot for each twin pair. So if this represents the x-coordinate, so it's the within a certain pair of twins, this is the brain size of the affected twin, and maybe this right here is the brain size of the non-affected twin within that same pair. Then for that set of twins, I draw a dot here. And for some other set of twins, I draw a dot here. And for some other set of twins, I draw a dot here. And you end up with one dot, not for each individual, but for each pair. That'll really be helpful, right? Because I can imagine drawing a line that represents affected equal to not, and you can count how many dots are above or below, right? In other words, in most twin pairs, is the schizophrenic brain bigger or smaller than the non-schizophrenic brain? The other thing you can do is make plots of the differences. So you can make a box plot of the differences, just one box plot now, or you can make a histogram of the differences. So again, just like I in the left side in the scatter plot have just one dot for each pair of twins, now I'm thinking of the data as just one data point for each pair of twins. So I take each pair of twins, I subtract schizophrenic brain size minus non-schizophrenic brain size. So now if there are, say, 14 sets of twins, I have 14 numbers, not 28. There are 28 people, but 14 sets of twins, perhaps. Then I have 14 numbers, and I can make a box plot of those. And maybe here's 0, and I might notice that, I don't know, maybe more than half of the pairs had positive differences, for example, right? Or maybe here's the 0. And I'm making up the data. This is a real data set, but I'm making up the patterns. Right? And so if you look at this histogram or this box plot, you can get a sense of whether the differences between schizophrenic and not are usually positive or usually negative. And that is vastly more informative than looking at the original 2 plots that I've crossed out, because the pairs are taken into account. So now we don't have to worry about the variation between the football players and the very, very petite people. I don't have to worry that among my affected people, there's a football player, and among my non-affected people, there's a very, very, very petite person. Rather, each of the data points that I've graphed anywhere along the bottom is a difference within a pair. And so I don't have to worry about any differences that are between the pairs. So understanding how to graph pair data is an important concept. So what's a paired t-test then? How do we do that? Turns out you already know how to do it. Here's why. The paired t-test is identical to a one sample test of the within pair differences. Okay? So if you have 28 people, but they're in 14 pairs, think of it as 14 data points, where each data point's value is equal to the difference within that pair. Again, I have 28 people that each have a different brain size. within each of the 14 pairs, I subtract, and now I have 14 numbers. And what I'm going to do is a t-test where the null hypothesis is that the mean brain size is the same in each group, or I can write it this way: the mean of the within pair differences is equal to 0. That's the same thing, right? Saying the mean brain size among the schizophrenic population and is the same as the mean brain size among the non-schizophrenic population. That's the same as saying if I take twins where one's schizophrenic and one's not and subtract, on average I'll get 0, right? That's the same thing. But this right here is the population mean of the within pair differences. Again, the key insight here, I'm going to keep repeating it, the key insight here is you take your paired data, and instead of thinking about the sample size being equal to the total number of units in both groups, instead your sample size is now the number of pairs. And instead of the data being equal to the original brain sizes, now your data is equal to the difference within each pair. So you've sort of cut your sample size in half, except you've vastly increased your ability to learn from this data, because by subtracting and focusing on the differences, you are removing the variability within the different twins. So we're going to do a one sample t-test, which is the same as a paired test. How do I do that again? Well, the t statistic is equal to the mean of the differences, okay, which is the same as saying the difference in means, right? Pause and think about that numerator. If I have these 14 pairs of twins, I could say, what's the mean brain size among all the schizophrenic twins? Minus, what's the mean brain size among all the non-schizophrenic twins? Or I could take the difference within each pair and take the average of those differences. That's literally the same number, and that's what that numerator is. The denominator is a little bit newer though. I take the sample variance of the within pair differences and divide by the number of differences. So the number of pairs, and this is the sample variance of the differences. You have reduced your data into a set of within pair differences. And now you're doing a one sample test for whether the average of those within sample differences is 0. A paired t-test is identical to a one sample t-test on the differences. Let me put the t right here, so it's a one sample t-test. To drive this idea home, let me broaden a little bit and talk about how to do the t-test in R, even though we also have code on this elsewhere. I think it's useful to mention here. For the two sample t-test, how do you do it? Well, you've got t.test, you give it the vector from one group, the vector from the other group, maybe there's some other arguments, and maybe you want to pool, but there's an argument called var.equal, and that's either equal to true, all caps, or it's equal to false, depending on whether you want to assume the variances are equal. False. Let's spell false correctly. Okay. That's how you do the t-test. Of course, there's another way to do the t-test, which I think we know, which is you can do t.test, and then maybe there's, if your data is arranged not in terms of one vector of x's and one vector of y's, but instead an outcome variable and some other variable that's a grouping variable, then you can do it this way. And you can have the same thing with var.equals, et cetera, et cetera. All right, so let's pause actually. What's the difference between this format and this format? In the first one, your data comes such that you have one column of all the schizophrenic. Let me use a different example actually, because the schizophrenic ones are paired. One column of the Finch brains from 1976 and another column of the Finch brains from 1978. And so it will be straightforward to just mention those two columns in the t-test. Suppose instead, going to the second line here, that in your data set you have one column containing all of the Finch beak measurements and another column indicating whether each measurement was from 1976 or 1978. Now this is easier, right? Now you could say, okay, Z represents the Finch beak depths, that's that column, and G represents the indicator for whether it's 1978 or 1976. It's the same t-test, but depending on how your data is formatted, one or the other might be easier. Okay, but that's the 2 sample t-test. Here's the 1 sample t-test. It's just t.test, and then you give it your vector of values, right? And there's other optional arguments, but that's the main idea, okay? By default, it compares those values to a null of 0. In other words, the null that the mean, that these observations are drawn from a population that has mean 0. Now, what about the paired test? Let's write it in black so we're being consistent. Well, you could do this. You could do it the same kind of way you did before. So you could say t.test, vector of schizophrenic twins, comma, vector of non-schizophrenic twins, comma, paired equals true. That'll work. Or if the data is arranged differently, column of everybody's brain size, tilde, indicator for whether you're schizophrenic or not, right?